What if I told you that humanity's greatest journey has already ended? What if the flight to the moon was not the first step to the stars, but rather the last look beyond the prison cell from which we may never escape? We grew up on stories about conquering Mars, about colonies on Jupiter's moons and interstellar arcs rushing toward distant exoplanets. But what if all this is just a beautiful fantasy that shatters against invisible but indestructible walls? Why, in more than 50 years, have we not advanced a single centimeter beyond the modest lunar frontier? Is it only a matter of money and political will, as we are often told, or do there exist fundamental barriers, physical, biological, and perhaps even existential, that turn our solar system into an impregnable fortress and Earth into its only habitable tower? Today, we will try to look the truth in the eye. We will not talk about budgets and short-term missions. We will talk about the laws of the universe, which are the same for everyone, both for us and for any other hypothetical civilization. We will talk about the walls of our cosmic prison. And the main question we will try to answer is this a temporary confinement from which we will one day find a way out, or a life sentence? Let us talk today about a dream, the very one that is born in many of us in childhood, when we first look at the night sky and see a scattering of distant lights, a dream of traveling to these lights, of stepping onto the surface of another world. For the greater part of the 20th century, this dream seemed almost tangible. It seemed we were standing on the threshold of a new era, the cosmic era of humanity. And its culmination, its brightest symbol, was undoubtedly the Apollo program. We all remember these frames, a grainy black and white image, a clumsy figure in a spacesuit descending the ladder, the words of Neil Armstrong that forever entered history. At that moment, on July 21st, 1969, humanity seemed to have taken a decisive step beyond its cradle. The whole world, holding its breath, watched this triumph of will, science, and courage. And then the feeling was born that this was only the beginning, that Mars would follow the moon, then the moons of the gas giants, and then, perhaps, the nearest stars. But more than 50 years have passed, 50 years during which technologies have changed beyond recognition. We have devices in our pockets that surpass in their computing power all of NASA's computers of that era combined. We have created a global information network, decoded the genome, learned to peer into the farthest corners of the universe with the help of space telescopes. And yet, the farthest frontier that a human foot has reached is still there, on the dusty surface of our satellite, at a distance of only 1.3 light seconds from home. Why? To understand this, we need to rethink the legacy of Apollo itself. We need to admit that this greatest breakthrough was simultaneously the greatest illusion. The flight to the moon was not the first step into the ocean of space. It was a grandiose anomaly, a unique confluence of political, technological, and human circumstances. At its core, it was a sprint. Incredibly expensive, dangerous, and complex, but still a sprint over a very short distance by cosmic standards. Imagine that all of humanity lives on the shore of a vast ocean, and then one day, the best, the bravest of us, using all available resources, were able to jump off the pier and touch the water with their feet, and then immediately return to land. Would this mean that we are ready to cross this ocean? Of course not. The flight to the moon was that very jump from the pier, and a flight to Mars, the nearest planet to us, is already an attempt to cross the Atlantic in a rowboat, and a journey to the stars is an attempt to swim to another galaxy. The scales are completely incomparable. The Apollo missions were designed with one goal: to reach the moon, stay there for a very short time, just a few dozen hours, and return as quickly as possible. The entire architecture of the mission was subordinate to this task. The astronauts were outside Earth's protective magnetic field for a minimal amount of time. They did not have time to receive a critical dose of radiation. Their bodies did not have time to fully feel the destructive effects of weightlessness. The psychological load, though colossal, had a clear and temporally imminent end. It was a daring sortie, but not a settlement. And herein lies the root of the illusion. We looked at this sortie and decided that now we know the way. But we were mistaken. There is another aspect that formed our false perception. This is the famous photograph, Blue Marble, taken by the crew of Apollo 17 in 1972. One of the most reproduced images in history. On it is our planet. An ideal, fragile, shining sphere against a background of absolute blackness. This image gave rise to the so-called overview effect, a deep existential experience, a feeling of unity with the planet, an awareness of its vulnerability. This is all true. But this image also had a reverse, unintended side. It made space cozy. It turned it into a background, a beautiful backdrop for our home. Looking at this photograph, one subconsciously feels that Earth and space are something commensurable. Here is the planet, and here is the void around it. It seems that one only needs to push off a little harder, and you are already flying to explore this backdrop. But this is a trick of perspective. Culture only intensified this deception. Recall Stanley Kubrick's film, 2001, A Space Odyssey, released a year before the moon landing. In it, space travel is shown as something routine. Huge stations in orbit, regular flights to the moon, elegant stewardesses in zero gravity. Kubrick's film influenced our imagination so strongly that we accepted his vision as a completely achievable future. We believed that the world of the Space Odyssey was a matter of the coming decades, and when Armstrong took his step, it seemed like a confirmation. Yes, we are on the right path, but reality turned out to be far more prosaic and cruel. Let us just look at the numbers, converting them into words we understand. The distance to the moon is about 384,000 kilometers. It sounds like a lot, but this is our nearest neighbor. The distance to Mars, when it is at its closest approach to Earth, is about 56 million kilometers. That is, even in the best case, Mars is more than 145 times farther than the moon. This is not a quantitative, but a qualitative change in the task. It is like comparing a walk to a neighbor's house with a trip around the world. Completely different technologies are required, a different approach to life support, to protection from danger, to the psychology of the crew. Everything that worked for the lunar sprint is absolutely inapplicable for the Martian marathon. Thus, the echo of Apollo still misleads us. We look at this great achievement of the past and incorrectly extrapolate it to the future. We think that since we could do it then, we can do it now. We just need more money and political will. But the problem is deeper. We are not facing an engineering task that can be solved by investing more resources. We are standing before a wall of fundamental laws of physics and biology. And the first, the most solid masonry in this wall, against which the dreams of many generations of engineers have shattered, is the tyranny of the simple, but inexorable rocket equation. But more on that in the next chapter. So, we admitted that the flight to the moon was a unique sprint and not the start of a marathon. But why? Why can we not simply build a bigger rocket, pour more fuel into it, and set off, say, to Mars? The answer to this question was given long before man built the first rocket at all. It was derived by pen on paper in 1903 by a Russian self-taught scientist, a deaf teacher from Kaluga, whom we know as Konstantin Eduardovich Tsiolkovsky. And this legacy, known as the Tsiolkovsky rocket equation, simultaneously opened the way to space for us and became our eternal curse. At first glance, the idea of a rocket is simple to the point of genius. Newton's third law, action is equal to reaction. We throw mass in one direction with great speed and receive acceleration in the opposite one. That is it. But as often happens, the devil is in the details, and Tsiolkovsky's equation reveals these details with ruthless directness. I will not present the formula itself here. We do not need it. Its essence is important to us, and its essence is simple and tragic. To change the speed of your ship, you need to throw away part of its mass. But here's the problem. The fuel that you have not burned yet is also part of the mass of your ship. It turns out that at the very beginning of the flight, you have to spend a huge amount of energy just to drag the fuel with you that you will burn at the very end. Let us imagine this with a simpler example. Imagine that you are a traveler who is going on a hike through a vast desert. The path will take 100 days. There is nowhere to get food along the way, so you must carry all the food for 100 days on yourself in a backpack. On the first day, your backpack is unbearably heavy. You take a step, and almost all the energy you spend goes not to moving forward, but simply to holding the weight of the food for the remaining 99 days on your shoulders. On the second day, the backpack will become slightly lighter, but you are still dragging provisions for 98 days, and so on. Most of your strength will be spent not on the journey itself, but on carrying the food for this journey. And now, let us transfer this analogy to a rocket. The rocket is our traveler, and the fuel is its food. 90 and sometimes 95% of the starting mass of a big rocket, like the legendary Saturn V, which carried astronauts to the moon, is fuel. Just imagine this visually. A huge 100-meter tower the size of a 36-story building, and almost all of it is tanks with kerosene, liquid oxygen, and liquid hydrogen. And at the very, very top of this titanic barrel of fuel is perched a tiny capsule with people and equipment, making up a negligible fraction of a percent of the total mass. Everything else is fuel, and engines to burn this fuel, and tanks to store this fuel. Rockets are, in essence, a way to deliver fuel into orbit in order to then burn it and fly further. This is the tyranny of the rocket equation. It demonstrates to us the so-called logarithmic dependence. This means that for each subsequent linear increase in speed, you require exponentially more fuel. Want to double the final speed of the ship? You will need not twice as much fuel, but many, many times more. Want to increase it 3 times? The mass of your rocket will grow to completely absurd astronomical values. That is exactly why rockets have stages. We discard the empty tanks and heavy engines of the first stage to lighten the construction and make the work of the second stage more efficient. Then we discard the second. This is a desperate attempt to somehow cheat the equation by getting rid of dry mass during the flight. Let us talk about such a concept as delta V, or characteristic velocity. This is, if you will, the currency of space travel. It is the total change in speed that your ship can provide. You have a certain budget of delta V, and you spend it on every maneuver. Need to get into Earth orbit? This costs very dearly, about 9.4 kilometers per second. Need to go to the moon? Spend another approximately 3.1 kilometers per second. Brake at the moon to enter its orbit? A little more from your budget. Land, take off, return. Every step requires spending. So the budget needed for a mission to Mars is incomparably larger than the lunar one. You need a huge delta V. Not only to fly there in an acceptable time, say, in 6 to 9 months. You need even more to brake at Mars, because it has a rarefied atmosphere, and simply entering it for braking, as ships returning to Earth do, is extremely difficult and dangerous. Then you will need fuel to take off from Mars, and then for the return trip to Earth. And all this fuel for braking at Mars, for life on its surface, for takeoff, and for return, you must bring with you from Earth. Which means, according to the Tsiolkovsky equation, your starting rocket must be not just big, it must be monstrously, implausibly huge. Or you will have to assemble the ship in orbit from dozens of separate launches, which turns the mission into a logistical nightmare costing trillions of dollars. But maybe we can just create more efficient engines? Unfortunately, here too, we hit a wall. The chemical rocket engines we use work at the limit of the possible. Their efficiency is determined by the speed of the outflow of gases from the nozzle. This is called specific impulse, and this speed, in turn, is limited by the energy that is released during the chemical reaction of combustion. We can select more exotic and dangerous types of fuel. We can improve the design of nozzles and turbopumps, but we will never be able to jump above our heads. The laws of chemistry tell us no more energy can be squeezed out of these molecules. This is a physical limit. To overcome it, completely different physical principles are needed. For example, nuclear engines, which we will talk about later, but even they do not solve all problems. So, what do we have in practice? Due to the tyranny of the rocket equation, we are forced to fly to other planets not in a straight line, but along so-called Hohmann transfer trajectories. These are elliptical orbits that require minimum fuel expenditure. We sort of roll out onto a higher orbit around the Sun and wait until Mars itself arrives at the desired point. This is economical, but very long. 6, 8, 9 months one way. And then, having arrived on Mars, one cannot simply turn around and fly back. One needs to wait for the next window when the planets again occupy a favorable position for the same economical flight. And this waiting can take more than a year. As a result, the entire mission to Mars with a return stretches for 2 or even 3 years. 3 years in a small metal capsule. And all this time, the ship must be absolutely reliable, because no help will come from Earth. And all this time, it must carry supplies of air, water, food, spare parts, and of course fuel for the return. Each kilogram of supplies added on board means that at the start on Earth, tens, if not hundreds of kilograms of fuel must be added. The Tsiolkovsky equation turns every trifle into an unbearable weight. That is why, when we hear bold statements about the imminent colonization of Mars, it is worth treating them with healthy skepticism. We are not talking about a lack of will or funding. We are talking about the fact that we are trying to cross an ocean on a vessel that spends 95% of its volume on transporting its own fuel, leaving only a tiny closet for the crew and cargo. This is the first wall of our prison. It is invisible. It consists of formulas and laws of chemistry, but it is stronger than any steel. But let us imagine for a moment that we were able to overcome it. Imagine that we built this Leviathan, this gigantic rocket capable of taking us on a 3-year journey. We solved the mathematical problem, and here our ship leaves the protective cocoon of Earth's magnetosphere and goes into open space, and immediately collides with the second wall. Invisible, silent, but absolutely deadly. This wall does not care how big your rocket is or how perfect its engines are. This is a wall of pure, hard radiation. When we say space, we often imagine emptiness, absolute nothingness, a vacuum, darkness between planets and stars. And this is one of the most dangerous misconceptions. Space is not empty. It is filled with an invisible and silent ocean of high-energy particles that pierce everything in their path. Here, on Earth, we live at the bottom of this ocean, reliably covered by a double shield. The first layer is our planet's magnetosphere, an invisible force field that deflects most of the charged particles flying from the sun. The second layer is our dense atmosphere, 100 kilometers thick, which serves as the final barrier, absorbing almost everything that broke through the magnetic field. We evolved in this safe bubble, in this quiet shelter, and any prolonged flight beyond its limits is like a deep-sea fish suddenly finding itself on sun-drenched land. Death is inevitable. It is only a question of time. Let us break down the threats in order from near to far, from less dangerous to the most insidious. The first obstacle that any interplanetary ship needs to overcome is the Van Allen radiation belts. These are 2 giant donuts of charged particles, protons, and electrons trapped by Earth's magnetic field. They surround our planet, and the radiation level in them is extremely high. Astronauts of the Apollo missions crossed them at very high speed, spending only about 30 minutes in the most dangerous zones. It was like a quick run through a burning house. Yes, dangerous. But if you move very fast, you can manage to slip through while receiving an acceptable dose. But if one lingers in these belts or crosses them repeatedly, for example, when assembling an interplanetary ship in a high orbit, the accumulated dose of radiation will become a serious problem even before the start of the journey itself. The Van Allen belts are, if you will, a moat of fire around our castle. Suppose we crossed it. The ship entered the trajectory to Mars. What next? And next, we fall under the power of the sun. Our luminary is not just a calm source of light and heat. It is a giant thermonuclear reactor that from time to time shows its violent temper. We are talking about solar flares and coronal mass ejections. As a result of such events, the sun can spew into space a giant cloud of protons accelerated to colossal energies. This is called a solar proton event. For the crew of an interplanetary ship, this is like a sudden, unpredictable tsunami in the middle of the ocean. If such a cloud covers the ship, the radiation level inside can jump hundreds and thousands of times in a matter of minutes. Without a special, very massive radiation shelter inside the ship, a compartment with thickened walls where the crew must hide for several hours or even days, such a flare can lead to acute radiation sickness and death in just a few days. The problem is that these events are almost impossible to predict in advance. They can happen at any moment. And the flight to Mars, let me remind you, takes many months. The probability of getting caught in such a radiation storm during the mission is very high. But even if we are lucky and the sun behaves calmly throughout the flight, we will still not be safe, because there exists a third, the most important and most inexorable radiation threat. These are galactic cosmic rays, or for short, GCR. This is that very wall that we, perhaps, will never be able to overcome. Unlike solar protons, which come from one nearby source, galactic rays fly at us from everywhere. Their sources are supernova explosions, active nuclei of distant galaxies, neutron stars, and black holes. These are the most powerful and violent processes in the universe, working as giant natural particle accelerators. What is a galactic cosmic ray? It is not just a proton or an electron. Most often it is the nucleus of an atom, completely stripped of its electron shell. It can be a nucleus of helium, carbon, oxygen, or even iron. And the most terrifying thing is that these nuclei are accelerated to energies that we can barely reproduce even in our most powerful accelerators, like the Large Hadron Collider. They rush through space at a speed constituting 99.9 or even more % of the speed of light. Imagine a microscopic but incredibly heavy and fast projectile. When such a particle, for example, an iron nucleus, crashes into the hull of a ship, it does not just pierce it, it knocks out a whole cascade of secondary particles, neutrons, mesons, and other nuclear fragments. As a result, a single GCR projectile hitting the ship spawns a real shower of secondary, no less dangerous radiation inside. A paradoxical situation arises. The thicker you make the protection, the more secondary radiation you can generate inside. It is like trying to stop a bullet flying at the speed of a bullet with a wall of glass. The bullet might stop, but you will be struck by a cloud of glass shards. It is practically impossible to effectively protect against galactic cosmic rays using passive armor. Calculations show that for a significant reduction in dose, protection made of several meters of lead or tens of meters of water or polyethylene would be needed. Imagine a spaceship whose walls have a thickness of several meters. According to the Tsiolkovsky equation, which we discussed in the previous chapter, the mass of such a ship will become so exorbitant that it will be impossible to move it from its place. This is how two walls of our prison, the mathematical and the radiation one, support each other. What are the biological consequences? Here we move from physics to medicine. Constant background bombardment by galactic rays over a multi-month flight is not the same as a short-term high dose that can be received during an accident at a nuclear power plant. This is a completely different type of impact. These heavy, high-energy nuclei cause irreparable damage at the cellular level. They stitch through DNA chains, causing mutations that the body's immune system is unable to fix. The main target is the central nervous system. Neurons, brain cells, practically do not regenerate. Every hit of a heavy element nucleus into the brain is the guaranteed death of a whole group of neurons. Studies conducted on rodents that were irradiated with doses equivalent to a Martian mission showed depressing results. The animals exhibited serious cognitive impairments, memory deterioration, inability to learn, loss of curiosity, increased anxiety. In essence, this is accelerated aging of the brain, which scientists have called space dementia. And this happens at doses that do not cause obvious symptoms of radiation sickness. A person may feel normal, but their brain will slowly and irreversibly degrade. Imagine a crew of astronauts who, after 9 months of flight, arrive at Mars, but are no longer capable of performing complex tasks, reacting adequately to emergency situations, and making correct decisions. This is a mission doomed to failure. Besides the brain, other systems suffer, for example, the lens of the eye, which leads to the development of cataracts. The cumulative effect on the DNA of all body cells repeatedly increases the risk of developing oncological diseases in the future. Data from the Curiosity rover, which measured the radiation background on the way to Mars and on its surface, confirmed the worst fears. During a mission to Mars and back, not counting the stay on the surface, an astronaut will receive a radiation dose of about 660 millisieverts. This is roughly 330 times more than the average annual dose a person receives on Earth from all sources. This is a dose that guaranteed exceeds all established limits for nuclear industry workers for their entire career. And this is assuming a calm sun. A single powerful flare can double or triple this figure. Thus, the ocean of radiation in which we intend to swim poses not just an engineering, but a fundamental biological problem. We are creatures created for life under the protection of an atmosphere and a magnetic field. Our biology is incompatible with open space. And until we invent some form of active protection, for example, an artificial magnetic field around the ship, and this is a technology from the realm of science fiction requiring an incredible amount of energy, any flight further than the orbit of the moon will be a game of Russian roulette. Even if you win and return alive, your body and your mind will never be the same. This wall of invisible particles seems almost insurmountable, but let us assume that we were able to bypass it too, created a fantastic ship with active protection and solved the radiation problem. But even inside this safe cocoon, our body, accustomed to the constant gravity of Earth, will begin to rebel. And this rebellion of biology will become our next, no less solid wall. Imagine a perfectly tuned mechanism that was created and refined over nearly 4 billion years to work in very specific conditions. Every part of it, every system fits one single unchanging constant: gravity. Earth's gravity, which we denote as 1g, is not just a background against which our life flows. It is the fundamental architect of our body. Our bones have exactly such density to withstand weight. Our muscles possess exactly such tone to resist gravity and move the body. Our cardiovascular system is calibrated to pump blood up to the brain, overcoming its tendency to drain down. Our entire organism, from cell membranes to the vestibular apparatus, is permeated by this constant, all-pervading influence. And now let us take away this constant, place this perfectly tuned mechanism in conditions of weightlessness, or, to speak more precisely, microgravity. What will happen? The mechanism will not just experience discomfort, it will begin to slowly but steadily dismantle itself. This is the fourth wall of our cosmic prison, the rebellion of our own biology, which refuses to function in an environment for which it was not created. We have heard a lot about the most obvious problems. First of all, this is muscle atrophy and loss of bone mass. In conditions of weightlessness, the body decides that a powerful skeleton and strong muscles are no longer needed. Why waste precious resources on maintaining what is not used? And it starts the process of dismantling. Muscles, especially the muscles of the legs and back, which on Earth constantly fight gravity, begin to rapidly lose volume and strength. Bones stop renewing. The body begins to actively leach calcium from them, which gets into the blood and is excreted through the kidneys, creating, by the way, an increased risk of kidney stones. Cosmonauts on the International Space Station fight this phenomenon by spending 2 to 2.5 hours a day on special exercise machines, treadmills with pull-down straps, cycle ergometers, and resistance machines. This allows slowing down the process, but not stopping it completely. Even with the most intensive training, bone mass loss is about 1 to 1.5% per month. For comparison, in an elderly person on Earth suffering from osteoporosis, this figure is about 1 to 2% per year. That is, in a year in orbit, An astronaut ages from the point of view of the skeleton by 10 or even 20 years. After a 6-month mission on the ISS, cosmonauts require a long rehabilitation period on Earth to recover. And now imagine a mission to Mars that will last about 3 years. Even with the best training regimens, by the time of arrival on the red planet, where gravity is about 38% of Earth's, the astronauts will be so weakened that the slightest awkward movement or fall could lead to a serious fracture. Their skeletons will become fragile, like those of very old people. But this is only the tip of the iceberg. There are also less known, but far more disturbing consequences. One of them is the redistribution of fluid in the body. On Earth, gravity pulls blood and other fluids down. Our cardiovascular system is adapted to this and constantly works to ensure sufficient blood supply to the brain. In zero gravity, this vector of force disappears. Fluid rushes to the upper part of the torso and into the head. Hence the characteristic puffiness of the face in astronauts in the first days of flight, nasal congestion, headaches. But this is not just a cosmetic effect. Increased intracranial pressure begins to exert an influence on the most delicate and sensitive organs, primarily on the eyes. Several years ago, NASA doctors encountered a mysterious phenomenon which is now known as SANS, or spaceflight-associated neuroocular syndrome. In many astronauts returning from long expeditions, deterioration of vision was found that did not pass even after returning to Earth. Detailed examination showed that increased pressure of fluid inside the skull literally flattens the back wall of the eyeball, causes swelling of the optic nerve disc, and leads to changes in the structure of the retina. This is not just nearsightedness that can be corrected with glasses. This is a structural deformation of the organ of vision, and to date, we do not know if these changes are fully reversible. We do not know what will happen to a person's vision after 3 years in weightlessness. Perhaps they will arrive on Mars practically blind. The cardiovascular system also suffers. The heart is a muscle. In zero gravity, it no longer needs to pump blood upward with effort. The load on it decreases, and it, like any other muscle without load, begins to weaken. It decreases slightly in size. Its shape becomes more spherical. The volume of circulating blood in the body also decreases. The body adapts to new, easy conditions. But what will happen when the ship lands on Mars, and the heart suddenly finds itself again in conditions of, albeit weakened, but still gravity? Will it be able to cope with the increased load? There's a high probability of orthostatic collapse, that is, a sharp drop in blood pressure and loss of consciousness when attempting to stand up. Let us go further to an even deeper level. Our immune system. Research shows that in conditions of spaceflight, it works worse. The activity of T lymphocytes, key cells of our immunity, decreases. Viruses dormant in the body, for example the herpes virus, can reactivate. Susceptibility to infections increases, and wound healing occurs slower. In conditions of the confined space of a ship, where the same microbes circulate, any, even the most harmless infection, can become a serious problem for the entire crew. And there is no ambulance to call. The first aid kit on board is all one can count on. Even such seemingly basic things as digestion and taste sensations change. Due to the influx of fluid to the head, astronauts constantly have a stuffy nose which dulls the sense of smell, and as a consequence, taste. Food seems bland and tasteless. This is not only a psychological but also a physiological problem, as it can lead to loss of appetite and insufficient calorie intake, which will further aggravate muscle atrophy. The totality of all these factors, loss of bone and muscle mass, vision problems, weakening of the heart, malfunctions in the immune system, paints a joyless picture. The human body is a product of Earth's evolution. It perceives weightlessness as a systemic failure, as a pathology. It tries to adapt, but this adaptation is, in essence, slow self-destruction. We can improve our ships as much as we like, make them reliable and fast, but we cannot change our own biology. We are locked in it, as in a spacesuit that cannot be removed. Perhaps the solution could be artificial gravity created by the rotation of the ship. This idea, familiar to us from science fiction, huge rotating station rings, is indeed the only known way to combat all these problems simultaneously. But here, we again return to engineering and energy difficulties. Creating a sufficiently large rotating module to avoid unpleasant side effects from the Coriolis force is a task of colossal complexity and mass, which means we again run into the tyranny of the rocket equation. The circle closes. The biological wall turns out to be no less strong than the radiation one. Even if we deliver a person to Mars alive and healthy from the point of view of radiation safety, they will arrive there weakened, fragile, with deformed eyes and a weakened heart. And we have not yet touched upon the most complex and unpredictable aspect, the human psyche, locked for 3 years in a metal box in the middle of an infinite void. Until now, we have talked about matter, about the mathematics of motion, about particle physics, about the chemistry of our body. But a human is something more than just a set of biological systems. Our mind, our consciousness, our self-sensation. All this is a product not only of internal biochemistry, but also of the external environment. We are creatures of context. We are shaped by landscapes, sounds, smells, the change of day and night, seasons, the feeling of solid ground under our feet, and the boundless sky overhead. We evolved in the embrace of the biosphere, and our entire psyche is calibrated to its rhythms and signals. And now let us imagine that we take all this away, absolutely everything, and place the human mind in an environment that is the complete opposite of Earth's. Not just into isolation, but into total sensory and existential deprivation. A spaceship flying to Mars is not a luxurious liner from Kubrick's films. It is a cramped, functional capsule stripped of everything superfluous. The living volume per crew member in the best case will be comparable to the volume of a small closet. In this space, one will have to live, work, eat, sleep, and communicate with the same few people for 3 years. 3 years. Try to imagine this not abstractly, but at the level of sensations. Every day you wake up and see the same walls, the same instruments, the same faces. The food is freeze-dried and monotonous. The sounds are the monotonous hum of life support systems and ventilation. The smells, a mixture of metal, plastic, and sweat. The view from the porthole. The first weeks, perhaps, it will be mesmerizing, but very soon it will turn into a static, unchanging picture. A black abyss, strewn with cold, unblinking points of stars. And most importantly, the view of Earth. At the beginning of the journey, it will give comfort. Here it is, our home, a blue marble becoming smaller and smaller. This image, known as the overview effect, is often described by astronauts as a spiritually transforming experience. But what happens when this marble turns into an unremarkable little star, indistinguishable from hundreds of others? And then, when the ship turns around for braking, disappears from the field of view altogether. Psychologists believe that at this moment a profound existential crisis may occur. The loss of visual connection with home is not just a symbolic act, it is the breaking of the last thread connecting a person with their world, with 7 billion other people. with all history and culture. It is the realization of absolute, unprecedented loneliness. You're the most distant exile in the history of humanity. No one has ever been so far from home, and no one can help you. Signal delay is another factor that we often overlook. Communication with Earth will not be instantaneous. Even at the closest approach of planets, a radio signal goes to Mars for about 3 to 4 minutes one way. This means that any dialogue turns into a painful exchange of monologues with pauses of 6 to 8 minutes. And when the planets are on opposite sides of the Sun, the delay will be more than 20 minutes one way. That is, 40 minutes for one cycle. Question answer. Imagine an emergency situation on board. You send a desperate request to Earth, and you need to wait 40 minutes just to receive confirmation that you were heard, not to mention advice. This delay creates an insurmountable psychological barrier. The crew is completely left to itself. They are not just far away, they are in another temporal reality. Communication with the Mission Control Center, which for astronauts on the ISS is constant support, will turn into something like archaeological correspondence. In such conditions, any, even the most insignificant interpersonal problem can grow to the scale of a catastrophe. We know this thanks to long-term isolation experiments on Earth, such as Mars 500, which was conducted in Moscow from 2010 to 2011. 6 volunteers spent 520 days in a closed complex simulating a flight to Mars, and the results were very revealing. Participants faced depression, apathy, sleep disturbances. Hidden and open conflicts arose, cliques formed. Some crew members practically stopped communicating with others, withdrawing into themselves. And these were the best of the best, carefully selected, highly motivated professionals who, moreover, knew that at any moment they could open the door and walk out. They knew what was on Earth. A real Martian crew will not have such an option. Let us add to this the constant stress from the awareness of danger. The ship is a fragile bubble of life in a deadly environment. Failure of a single system. A micrometeorite the size of a grain of sand piercing the hull. An error in calculations. And it is all over. This is not fear of height or speed, which one can get used to. This is a permanent background awareness that between you and instant death is only a few millimeters of metal and plastic. How long can the human psyche withstand such tension without breakdowns? Disruption of circadian rhythms is another serious problem. Our internal biological chronometer is tuned to a 24-hour cycle of day and night change. In a spaceship, this does not exist. There is only artificial lighting on a schedule. This leads to failures in the production of melatonin and cortisol, which causes insomnia, chronic fatigue, decreased concentration, and performance. And now imagine that after 9 months of such a flight, the crew arrives on Mars, where a day, the so-called soul, lasts 24 hours and 39 minutes. This small, seemingly difference will constantly knock off the already disturbed rhythms of the body, leading to a state of permanent jet lag. And finally, let us think about the return itself. Imagine that the mission was successful. The astronauts stayed on Mars, completed all tasks, and set off on the return journey. They returned to Earth after 3 years. During this time, the world they left has changed. Grandchildren were born whom they never saw. Their friends and loved ones lived 3 years of their lives, and they return weakened with undermined health, and they face a long and painful period of rehabilitation. Will they be able to integrate into society again, or will they forever remain strangers, people not of this world, marked by the seal of the abyss? The psychological price of such a journey may turn out to be exorbitantly high. The fifth wall is not concrete and not a force field. It is woven from the threads of our consciousness, from our need for belonging, for communication, for contact with nature, for a sense of safety. We can build the most perfect ship, but if we cannot preserve the sanity and humanity of the crew in it, it will turn into a flying sarcophagus. And until we understand fully how the human psyche works in conditions of absolute isolation and separation from home, any manned flight to Mars will be not so much a scientific expedition as a reckless psychological experiment with an unpredictable ending. But even if we solve all these problems, engineering, physical, biological, and psychological, we will collide with the last, the highest, and absolutely insurmountable wall. A wall that is built into the very fabric of the universe. This is the fundamental speed limit. Imagine a racetrack on which the fastest objects in the universe compete. On this track, there's an absolute, unsurpassed champion. This is the photon, a particle of light. Its speed in a vacuum is approximately 299,792 kilometers per second. This is not just a very high speed, it is a limit. A fundamental constant on which, as on a foundation, the entire building of modern physics is built. And the special theory of relativity, formulated by Albert Einstein in 1905, passes a final and unappealable sentence on us. Nothing having rest mass, be it a spaceship, a planet, or you yourself, can ever reach this speed. Even approaching it is an almost impossible task. Why? Why does this cosmic speed limiter exist? Our usual Newtonian logic fails here. We are used to thinking that if we constantly apply force to a body, it will accelerate indefinitely. If we push a car, it will go faster and faster as long as we have strength or fuel. But the universe is actually arranged much more cunningly. Einstein showed that mass and energy are two sides of the same coin, which is expressed in the most famous equation in the world, E equals mc squared. He also showed that the mass of an object is not a constant value. It grows with an increase in its speed. Let us conduct a thought experiment. We have a spaceship, and we start to accelerate it. At first, everything goes as usual. We burn fuel, and the ship's speed grows. But as we approach the speed of light, something strange begins to happen. The same portion of fuel, which in the beginning gave us a large increase in speed, now gives a smaller and smaller effect. Why? Because part of the energy from the burning fuel, instead of going to increase speed, begins to turn into the mass of the ship. The ship becomes heavier and heavier. Its inertia grows. To accelerate it even a little more and more energy is required. At a speed of 87% of light speed, the mass of the ship will double. At a speed of 99.5%, it will grow 10 times. And as we further approach the coveted limit, the mass will begin to tend toward infinity. And to accelerate an object with infinite mass, infinite energy is needed. Since we do not possess infinite energy, reaching the speed of light for a massive object is impossible. This is not a technological limitation that we will someday overcome. It is a fundamental law of nature. Light can move at such a speed only because its particles, photons, do not have rest mass. It is the exception that proves the rule. This speed limit turns our galaxy, not to mention the universe, into a place unimaginably huge and unattainable. Let us try to grasp these distances. We have already said that light reaches the moon in 1.3 seconds. To Mars, in the best case, in 3 to 4 minutes. To Jupiter, already in half an hour. And to the farthest outskirts of our solar system, to the hypothetical Oort cloud, light will fly for about a year. 1 light year. And what is beyond? The nearest star to us besides the Sun is Proxima Centauri. It is at a distance of approximately 4.2 light years. This means that even if we could fly at the speed of light, a one-way trip would take 4.2 years. But we cannot. The fastest man-made object ever launched by humans is the Parker Solar Probe. At the moment of closest approach to the Sun, it reaches a speed of about 190 kilometers per second. This is incredibly fast by Earth standards, but it is only 0.064% of the speed of light. If we launched the Parker probe towards Proxima Centauri, it would fly to it for about 6,600 years. 6,600 years. This is more than all recorded human history, from the invention of writing in Sumer to our days. And this is to the nearest star. And our galaxy, the Milky Way, has a diameter of about 100,000 light years. It contains, according to various estimates, from 200 to 400 billion stars. Even if we imagine a fantastic ship capable of flying at a speed of 10% of light speed, and this requires a completely unimaginable amount of energy, which we will talk about in the next chapter, a journey to the center of our own galaxy will take 250,000 years. And to the nearest large galaxy to us, the Andromeda Nebula, to fly takes 2.5 million years. The Wall of Light puts an end to the idea of an interstellar empire, to Star Wars and Star Trek. A galaxy is not a single space through which one can move quickly. It is an archipelago of hundreds of billions of star islands separated by an ocean of time that cannot be crossed in a single human life. But the theory of relativity prepared for us another strange and counterintuitive surprise. This is the so-called relativistic time dilation. The faster you move in space, the slower time flows for you compared to those who remained in place. This is not an optical illusion, and not a malfunction in clocks. It is a real property of space-time. If you went on a journey to Proxima Centauri on a ship flying at a speed of 99% of light speed, then for you on board, only about 7 months would pass. You would return to Earth having aged a little more than a year, but on Earth during this time, almost 8.5 years would have passed. Your children would become adults, your friends would age, and if one goes further, a journey to the center of the galaxy at such a speed would take for the crew only about 21 years. They could make it and return, but upon return, they would discover that 50,000 years had passed on Earth. Human civilization, which they knew, would have long ceased to exist. This effect, known as the twin paradox, turns any long space journey into a one-way ticket. Not in space, but in time. You cannot return to your world because it no longer exists. You become an alien from the past. Thus, the Wall of Light works in 2 directions. On the one hand, it makes interstellar distances insurmountably large from the point of view of an external observer, requiring millennia to overcome them. On the other hand, it cuts off any sufficiently fast traveler from their own timeline, turning them into an eternal exile. The universe, as it turns out, is huge, not only in space, but also in time. And these 2 quantities are inextricably linked. The fundamental speed of light limit is not a technical problem. It is a built-in property of the operating system of our universe itself, and it tells us a very simple thing. Your place is here, in your star system, everything that lies beyond its limits is separated from you by a barrier that you cannot overcome without paying for it with time, either your own or the time of the rest of the world. But let us for a moment forget about time and return to energy. We mentioned that accelerating to sublight speeds requires an unimaginable amount of it. How unimaginable? This question is so important that it deserves a separate detailed consideration. We established that the laws of physics forbid us from reaching the speed of light. But maybe we could at least approach it, say, accelerate to 10, 50, or even 99% of light speed? Technically, the theory of relativity does not forbid this. It only says that for this, very, very much energy will be required. But what is very much in the context of space? Let us try to calculate this and translate it into quantities understandable to us, and we will see that behind this modest very much hides a real energy abyss separating us from the stars. To begin with, let us return to our chemical rockets. We already found out that they are monstrously inefficient due to the tyranny of the Tsiolkovsky equation. The maximum speed they can give a ship is limited by the speed of gas outflow, and that, in turn, is limited by the energy of chemical bonds. Even the theoretical maximum for the most exotic chemical fuels is only a few tens of kilometers per second. This is enough for flights inside the solar system, but for interstellar travel, it is like trying to cross the Pacific Ocean on a turtle. We have already calculated that with such speed, flying to the nearest star takes thousands of years. So, chemical engines do not suit us. Fundamentally different energy sources are needed. Let us ascend to the next rung of the technological ladder, to nuclear energy. Here we are dealing not with the energy of chemical bonds, but with the energy contained within atomic nuclei. And it, according to that same equation, E equals mc squared, is orders of magnitude, millions of times greater. There are several concepts of nuclear rocket engines. The simplest is a nuclear thermal engine. In it, a nuclear reactor is used simply as a stove to heat a working fluid, for example, liquid hydrogen, which is then ejected from the nozzle at high speed. Such engines are about twice as efficient as the best chemical ones. This is already not bad for fast flights to Mars, but for stars, it is still too slow. A more advanced and ambitious idea was proposed in the 50s of the last century within the framework of Project Orion. The idea was daring and, in its own way, ingenious. Use a series of directed nuclear explosions as an engine. A small nuclear charge explodes behind the stern of the ship at a safe distance. The shockwave and plasma hit a massive pusher plate, which transfers the impulse to the ship through a system of shock absorbers. Then the next explosion, and more and more. The ship flies on a cushion of atomic bombs. Calculations showed that such a method could accelerate a huge ship of hundreds of thousands of tons to a speed of 3 to 5% of the speed of light. The journey to Proxima Centauri would be reduced from 6,600 years to about 100 years. This is no longer eternity, but still beyond the limits of one human life. In addition, Orion has obvious problems. Starting from Earth would be impossible due to radioactive fallout, and one would need to carry a supply of several thousand nuclear charges on board. But let us go even further. What can be more powerful than nuclear fusion? The reaction that powers our sun. Imagine a thermonuclear engine. It could use isotopes of hydrogen, deuterium, and tritium, which can be found in abundance, for example, in Earth's oceans, as fuel. The energy release in thermonuclear fusion is even higher than in nuclear fission. Theoretically, such an engine could accelerate a ship to 10 to 15% of the speed of light. the flight time to the nearest star would be reduced to 30 to 40 years. Now this seems like something achievable. A generation that started from Earth could reach the destination. But here too, a trap awaits us. We have not yet learned to control thermonuclear reaction on an industrial scale, even on Earth in stationary reactors the size of a house. To create a compact, reliable, and safe thermonuclear engine for a spaceship is a task whose complexity lies beyond the bounds of our current and, possibly, future technologies. But let us imagine that we solve this problem too. We have an ideal engine. There remains the most efficient of all conceivable ways of obtaining energy: annihilation, the meeting of matter and antimatter. In annihilation, 100% of their mass, according to E equals mc squared, turns into pure energy, mainly in the form of gamma quanta. This is the absolute theoretical limit. It cannot be more efficient. A ship with an annihilation engine could, according to the boldest calculations, reach a speed of 90 and even 99% of the speed of light. The flight time to Proxima Centauri for the crew would be only a few months. A dream, yes, but the price of this dream is colossal. Firstly, antimatter needs to be obtained somewhere. It does not exist on Earth. It needs to be produced in particle accelerators, literally piece by piece, one antiproton at a time. The amount of energy that needs to be spent on the production of 1 gram of antihydrogen exceeds the entire annual energy consumption of humanity. And for an interstellar flight, tons of antimatter will be needed. Secondly, it needs to be stored somehow. Antimatter cannot come into contact with ordinary matter, otherwise an explosion will occur. It needs to be held in special magnetic traps, in a vacuum at ultra-low temperatures. This is an incredibly complex and dangerous technology. The slightest failure in the containment system, and your ship along with the crew will turn into a blinding flash of gamma radiation. But let us now return to the most important thing, to the numbers. Let us calculate how much energy is needed to accelerate to a significant fraction of the speed of light. Even a small ship, say, with a mass of just 1,000 tons, which is comparable to the International Space Station. The kinetic energy of an object is calculated by the relativistic formula. And here is what it tells us. To accelerate our 1,000-ton ship to just 10% of the speed of light, an amount of energy comparable to what all humanity consumes in several months will be required. To 50% of the speed of light, already more than the entire annual world energy consumption. And to accelerate it to 99% of light speed, energy equivalent to the consumption of all humanity for several centuries will be needed. And this is only for acceleration. But the ship must also be braked at the destination, which will require exactly the same amount of energy. Here it is, the energy abyss. Interstellar travel is the most energy-consuming enterprise imaginable. It requires such an amount of energy that our entire civilization with all its power plants, oil fields, and reactors looks like a tiny battery against this background. To seriously think about such flights, a civilization must master energy sources of a planetary scale. For example, learn to effectively use all the energy received by the planet from its star. This is what futurist Nikolai Kardashev called a Type 2 civilization. We, meanwhile, barely reach Type 0.7 on this scale. This is a wall, an energy wall, possibly the highest of all practical ones. It tells us that as long as we are tied to the resources of one planet, the stars are close to us. And this leads us to a very interesting question. If this is so unimaginably difficult for us, why do we think it might be easy for someone else? If the universe has set such strict rules for everyone, Maybe this is where the answer to one of the most important questions of humanity lies. Why is space silent? So, we are standing before a wall, or rather, before a whole series of concentric walls built by the universe itself, the tyranny of the rocket equation, the deadly ocean of radiation, the rebellion of our own biology, the abyss of psychological isolation, the insurmountable speed of light limit, and finally, the chasm of energy costs. Each of these walls in itself seems almost impregnable. Together they form what we called our cosmic prison. And looking at these walls, it is easy to fall into despondency, to feel our isolation, our loneliness in space. But let us change the angle for a moment. Let us ask the question, are we definitely alone? And if not, then why do we not see traces of other prisoners? If getting out of one star system is so unimaginably difficult, maybe this is a universal rule? Maybe all civilizations in the universe are locked in their cradles just like us. This train of thought leads us to one of the deepest and most disturbing mysteries of modern science. It is known as the Fermi paradox, and its essence can be expressed in one simple phrase. Where is everybody? The history of this question is indicative in itself. It was the year 1950. The setting was the cafeteria of the Los Alamos National Laboratory in New Mexico, the cradle of the American atomic program. At the lunch table sat several leading physicists of that time: Emil Konopinski, Edward Teller, Herbert York, and, of course, Enrico Fermi himself, a Nobel laureate, one of the fathers of the nuclear reactor, a man who possessed a unique ability for quick and accurate estimates of the most complex problems on a napkin. The conversation at the table was about a recent series of cartoons in the New Yorker magazine, which amusingly played on the theme of the disappearance of trash cans in New York. They were, according to the plot, being stolen by aliens. The conversation flowed smoothly to the possibility of interstellar travel and the probability of the existence of extraterrestrial civilizations. After some discussion, the group returned to other topics, but Fermi, as eyewitnesses recall, suddenly broke the silence and asked his famous question, addressed not so much to the interlocutors as to the universe. But where is everybody? In this simplicity lies all the power of the paradox. Fermi, like any physicist, thought in scales. He understood that our solar system is relatively young. It is about 4.5 billion years old, while the age of our galaxy, the Milky Way, is more than 13 billion years. This means that billions of stars of the first and second generations existed in the galaxy, around which planets could have formed long before the appearance of Earth. Hypothetical civilizations that arose on these planets had a head start of hundreds of millions, or even billions of years compared to us. Let us imagine such a civilization that overtook us in development by, say, 1 million years. By the standards of the evolution of the galaxy, this is an instant, but for technological development, it is eternity. Try to compare our technologies today with the technologies of just a century ago. And now, extrapolate this progress 1 million years forward. The capabilities of such a civilization would be indistinguishable from magic to us. And this is where the paradox begins. Even if such a civilization is limited by the same laws of physics as we are, and cannot exceed the speed of light, this time is more than enough to leave a trace of its presence throughout the galaxy. Let us calculate. Suppose a civilization has mastered interstellar flight and sends colony ships to the nearest stars at a speed of just 1% of the speed of light. This is very slow and conservative. The journey to the nearest star will take several hundred years. Having arrived at the place, the colony settles in for several centuries, develops, and itself sends the next expeditions. Such a process of expansion, similar to how Polynesians settled the islands of the Pacific Ocean, turns out to be surprisingly fast in galactic scales. Calculations conducted by many scientists, including Carl Sagan, show that for the complete colonization of the entire Milky Way, by such a slow method, 5 to 50 million years would be required. 50 million years. Sounds long, but remember that this is only a small fraction of a percent of the galaxy's age. If at least one civilization had begun such expansion 1 billion years ago, their descendants, their robots, their artifacts would be everywhere today. They would be in our solar system. They would have discovered us long ago, studied us, and possibly left some sign. But we see nothing. Absolutely nothing. Space looks pristinely clean and lifeless. This is the great silence. To give this paradox a more rigorous form, the American astronomer Frank Drake in 1961 proposed his famous equation. The Drake equation is not a strict physical formula, but rather a probabilistic framework for thinking, a way to break one big question: how many civilizations are in our galaxy, into several small, more understandable questions. Let us go through its components. It tries to estimate the number of civilizations with which we could hypothetically establish contact. This number is equal to the product of 7 factors. The first is the rate of star formation in our galaxy. We know this value quite well. It is approximately 1 to 3 stars per year. The second, the fraction of stars possessing planetary systems. In Drake's time, this was pure hypothesis. Today, thanks to the work of space telescopes Kepler and TESS, we know that this fraction is very large, close to 1. Planets are not an exception, but the rule. Almost every star has its retinue. The third, the average number of planets in one system that are suitable for life. Here we enter the realm of assumptions. We are talking about the so-called Goldilocks zone, an orbit where it is neither too hot nor too cold for water to exist in liquid form. Estimates here vary greatly, but even the most modest say that there could be billions of such planets in the galaxy. The fourth, the fraction of planets on which life actually originated. This is one of the biggest question marks. We know only one example, our own. Optimists believe that if conditions are suitable, the origin of life, abiogenesis, is an almost inevitable chemical process. Pessimists, such as proponents of the rare earth hypothesis, argue that this required a unique confluence of dozens of unlikely circumstances. The fifth, the fraction of planets with life on which intelligence developed. Another riddle. On Earth, life has existed for almost 4 billion years, but technological intelligence appeared only in the last instant of this term. Dinosaurs ruled the planet for 150 million years and did not build a single radio telescope. Perhaps intelligence of our type is a rare evolutionary anomaly and not a logical outcome. The sixth, the fraction of intelligent civilizations that develop technologies allowing them to send signals into space. Dolphins or whales may be very smart, but without limbs for manipulating objects and without fire, they will never join the space club. And finally, the seventh, the most important and most ominous factor, the average lifetime of such a technological civilization. How long does it exist in a state where it is capable and willing to communicate? 100 years? 1,000? 1,000,000? Or does it inevitably destroy itself in a nuclear war? Exhaust the resources of its planet? or simply lose interest in space, immersing itself in virtual worlds. Even if we take the most pessimistic, most modest estimates for all these unknown factors, the Drake equation still most often gives a result greater than 1. It tells us that we should not be alone. In the galaxy right now, there should exist at least a few, and possibly thousands or millions of civilizations. And here we come to the essence of the Great Silence. We have been listening since the 60s of the last century. Projects searching for extraterrestrial intelligence known under the general name SETI scan the sky with radio telescopes. We are looking for signals that could not have a natural origin. Narrowband, structured, artificial. For more than 60 years of searching, we have found nothing. There was the famous WOW signal registered in 1977. A powerful narrowband burst that lasted 72 seconds and never repeated again. But a single unconfirmed signal in half a century is a deafening silence. We do not catch either purposeful messages or accidental leakage of their radio and television broadcasts. But maybe they do not use radio. Maybe they communicate using lasers, neutrinos, or gravitational waves, which we are only learning to detect. Possibly, but the absence of physical traces is harder to explain. If civilizations have existed for millions of years, some of them inevitably should have mastered mega engineering. Physicist Freeman Dyson suggested that an advanced civilization, to solve its energy problems, might build a sphere or a swarm of giant structures around its star to capture all its energy. Such a Dyson sphere would be invisible in the optical range but should glow brightly in the infrared due to re-radiation of heat. We look for such objects and do not find them. And what about robotic probes? The concept of a von Neumann probe implies the creation of a self-replicating spacecraft. It arrives in a star system, finds resources, for example, in the asteroid belt, builds copies of itself, and sends them to the next stars. Even one such probe, launched millions of years ago, could fill the entire galaxy with its descendants. We should have stumbled upon such a device in our own solar system. But the asteroid belt seems to consist only of rocks and ice. This is what the Fermi paradox consists of in its entirety. On the one hand, billions of stars, billions of years of time, and high probabilities saying that the galaxy should be teeming with life. On the other, absolute, total, deafening silence, and the absence of any traces. This discrepancy is so great that it demands an explanation, and one of the strongest explanations returns us to the beginning of our conversation. Perhaps the walls of our cosmic prison are not our unique problem. Perhaps this is a universal law. Perhaps there exists something that prevents civilizations from reaching the stage of galactic expansion, some barrier that almost no one can overcome. In science, this something has received the name Great Filter. And talking about it is a conversation about our own future. The idea of the Great Filter was formulated in the 90s of the 20th century by economist and futurist Robin Hanson. He approached the Fermi paradox not as an astronomer, but as a systems analyst. He said, "Let us look at the path from lifeless matter to an advanced civilization capable of colonizing the galaxy as a long chain of sequential steps. Here is an approximate list of these steps. First, the emergence of a suitable planetary system with a star of the right type. Second, the appearance on the planet of self-replicating molecules, such as RNA or DNA, the origin of life. Third, the development of simple single-celled life, prokaryotes. Fourth, the development of complex single-celled life, eukaryotes with a nucleus and organelles. Fifth, the emergence of multicellular organisms. Sixth, the appearance of animals with a complex nervous system capable of movement and thinking. 7th, the development of intelligence of our level, capable of creating tools, culture, language. 8th, the emergence of a technological civilization capable of global communication and space exploration. That is, this is us right now. 9th, the beginning of large-scale space colonization, going beyond the limits of one's star system. So, the Great Filter hypothesis states that somewhere on this path from the 1st to the 9th step, there exists one or several barriers that are practically insurmountable. This barrier is the filter. It is so complex that out of billions of potential starts of planets with life, only a few, or maybe none at all, can pass it. The great silence that we observe is the evidence of this filter's work. Space is empty not because we are alone, but because almost no one survives to the stage where they could become noticeable. And here, the most important and most disturbing question arises before us. Where in this chain are we? Where is humanity located in relation to the Great Filter? Logically, there are only 3 possible options, and each of them forces deep reflection. Option 1, the Great Filter is already behind us. This is the most optimistic and perhaps the most pleasant scenario for our self-esteem. It implies that one of the early steps in the evolutionary chain was incredibly, almost impossibly difficult. We, humanity, passed this filter, and now the path to the stars is open before us. We are the first, or one of the first, to do this. We are a unique phenomenon in the Milky Way. What could be such a filter? Perhaps the origin of life itself, a biogenesis. Maybe the transition from non-living chemistry to the first self-replicating molecule. This is an event with such negligible probability that it happened in our galaxy only once, here, on Earth. If this is so, then we can expect to find in space many planets suitable for life, but absolutely sterile. Or maybe the filter was the transition from simple prokaryotic cells to complex eukaryotic ones. This step on Earth took almost 2 billion years, half of the entire history of life. For 2 billion years, life on our planet was represented only by primitive bacteria. Perhaps this step, the emergence of the eukaryotic cell with its mitochondria and complex internal structure, requires such a unique symbiosis and confluence of circumstances that it is an insurmountable barrier for most worlds. If this scenario is correct, then the silence of space is good news. It means that we won the cosmic lottery. We are pioneers, and someday, perhaps, we will become those forerunners, that ancient civilization about which legends will be composed by new races, if they ever appear. In this case, a colossal responsibility lies on us not to interrupt this unique chain of life and reason. Option 2. We are passing through the Great Filter right now. This scenario is much more alarming. It assumes that we are in the middle of the most dangerous stage, that specifically the development of a technological civilization capable of going into space is that very barrier on which almost everyone stumbles. Why? Because the technologies necessary for space exploration almost inevitably give a civilization the means for self-destruction. Nuclear weapons were the first obvious candidate for the role of such a filter. A civilization discovers the energy of the atom to build starships, but manages to destroy itself in a global war earlier. This was a very popular hypothesis during the Cold War. Today, the list of potential filters of our time has expanded significantly. It could be uncontrolled climate change and the destruction of the biosphere. A civilization begins to burn fossil fuels for its industrial revolution, but does not manage to switch to clean energy sources in time before its planet becomes unfit for life. It could be the creation of artificial superintelligence that gets out of control and destroys its creators. It could be the development of genetic engineering leading to the creation of an artificial virus that destroys the entire biosphere, or even simply a collapse into an information singularity. A civilization creates virtual worlds so attractive that it completely loses interest in exploring the real, complex, and dangerous universe and slowly fades away in digital dreams. If this scenario is correct, then the silence of space is a grim warning. Every civilization reaching our level faces an exam, and judging by the silence, almost no one passes this exam. We are sitting in the exam room right now, and time is running out. Our future and the answer to the Fermi paradox depend on whether we can solve these existential problems in the coming centuries. Option 3. The great filter is still ahead. This is the darkest and most frightening scenario. It implies that all previous steps were relatively easy. Life originates often. Intelligence develops everywhere. Technological civilizations arise here and there, like mushrooms after rain. But there is something ahead, some barrier that we do not even suspect yet, and which guaranteed destroys everyone who reaches it. What could it be? Perhaps it is some law of physics unknown to us. For example, any attempt to create technology for interstellar travel, be it a warp drive or the use of vacuum energy, inevitably leads to a catastrophe of local scale, for example, to a collapse of space-time, or the creation of a microscopic black hole that devours the home planet. Or maybe it is something of cosmological scale, for example, periodic gamma-ray bursts from exploding stars that sterilize whole sectors of the galaxy every few 100 million years. Civilizations simply do not have time to develop to the stage of interstellar expansion before a wave of deadly radiation covers them. We perhaps simply live in a short period of calm. Or, and this is the most sinister version, the filter is the older civilizations themselves. The dark forest hypothesis, popularized by Chinese science fiction writer Liu Cixin, suggests that the universe is like a dark forest full of hiding hunters. No one knows the intentions of another. Any signal sent into space is like a shout in the forest that betrays your location. And since resources are limited, and the development of another civilization is unpredictable, the safest strategy for anyone is to immediately destroy any other civilization as soon as it becomes noticeable. In this scenario, the great silence is not the silence of an empty theater. It is the hushed silence of a predator listening to the slightest rustle. And we, having started sending radio signals into space, may have already made a fatal mistake. In the context of our conversation about the walls of the cosmic prison, the great filter hypothesis offers the most radical explanation. Perhaps all those walls we discussed, radiation, the tyranny of the rocket equation, biological limits, are components of this filter. Perhaps their combined complexity is so great that overcoming them all together is beyond anyone's power. They do not just limit us, they protect the galaxy from us, and us from the galaxy. They ensure that life originating in one cradle remains in it. But the human mind is designed in such a way that it always looks for loopholes. Even faced with the most fundamental prohibitions, we begin to ask, but what if? But what if one does not have to fly through space, but somehow bypass it? What if one can hack the geometry of the universe itself? These bold, almost insane ideas, born at the junction of general relativity and quantum mechanics, will be the topic of our next chapter. So, we admitted that within the framework of known physics, within the framework of special relativity, Interstellar travel is either a millennial odyssey or a one-way ticket in time. The direct path through space is essentially closed to us. But what if one does not need to break through the wall? What if one can find a secret door in it, or dig a tunnel under it? Exactly such workarounds are offered to us by another great theory of Einstein, the general theory of relativity, or GTR. If the special theory of relativity established the rules for the motion of objects in space-time, then the general theory of relativity describes space-time itself as something dynamic, flexible, capable of bending and deforming under the influence of mass and energy. Gravity, in the view of GTR, is not a force attracting bodies, but a curvature of the fabric of space-time. Massive objects such as planets and stars press down on this fabric, similar to how a heavy ball presses down on a stretched rubber sheet, and other objects simply roll along these curves. This idea about the flexibility of the universe itself opens up hypothetical loopholes for us. Loophole 1. Wormholes or Einstein-Rosen bridges. Imagine that our three-dimensional space is just the surface of a huge sheet of paper. To get from point A to point B, we need to crawl along the surface of this sheet. This is a long way, but what if we can bend the sheet so that points A and B end up right above each other, and then pierce the sheet with a needle, creating a tiny tunnel connecting these 2 points directly? The path through this tunnel will be incomparably shorter than the path along the surface. This is the essence of a wormhole. This is a hypothetical tunnel in space-time that connects 2 very distant regions of the universe, and possibly even 2 different universes. For the first time, such a possibility was mathematically described back in 1935 by Albert Einstein himself and his colleague Nathan Rosen. They showed that GTR equations allow for the existence of such structures, which they called bridges. True, the original Einstein-Rosen bridges were absolutely impassable. They existed only for an instant, and then collapsed faster than even a photon could fly through them. In addition, they were closely related to the mathematical description of black holes and represented more of a mathematical curiosity than a real way of travel. The idea gained a second wind in the 80s of the 20th century, thanks to astrophysicist Carl Sagan. When he was writing his famous science fiction novel Contact, he needed a plausible way for his characters to quickly move to the star Vega. He turned for consultation to his friend, the prominent theoretical physicist Kip Thorne. Thorne, interested in the task, performed calculations and came to the conclusion that theoretically one can imagine a traversable wormhole. But for this, one very specific and very strange condition is required, so that the throat of such a tunnel does not collapse under the action of its own gravity. It needs to be propped open by something that possesses anti-gravity. That is, something that has negative energy density, or, simply put, negative mass. Here is where we leave the realm of, albeit complex but still understandable physics, into the realm of pure hypotheses. Such a substance has received the name exotic matter. We have never observed anything like it in nature. All particles and fields known to us have positive or zero energy density. The existence of exotic matter does not contradict some sections of quantum field theory. For example, the Casimir effect demonstrates regions with energy density lower than that of a vacuum. But the possibility of assembling a macroscopic object from this capable of holding open a whole wormhole remains absolutely speculative. Even if we imagine that exotic matter exists and we learn to work with it, the problems do not end there. How to create a wormhole? How to pull its second end to the desired star system? What will happen to a traveler passing through a region with such extreme gravitational fields and exotic matter? And also, as further calculations showed, the creation of a wormhole can lead to the emergence of a so-called time machine, which generates a whole bouquet of logical paradoxes with causality, like the famous grandfather paradox. Many physicists, including Stephen Hawking with his chronology protection conjecture, believe that the laws of nature must somehow forbid the creation of such structures to preserve the logic of the universe. Thus, a wormhole is a beautiful, elegant mathematical idea, but its physical implementation requires such a number of assumptions and collisions with such fundamental problems that it will most likely remain forever in the world of science fiction. Loophole 2. The Alcubierre drive, or warp drive. If a wormhole is a tunnel through space-time, then the Alcubierre drive offers another, no less elegant trick. Instead of moving in space, it forces space itself to move around the ship. This concept was proposed in 1994 by Mexican theoretical physicist Miguel Alcubierre. He showed that there exists a solution to Einstein's equations that describes the following. One can create a bubble of distorted space-time around a spaceship. In front of this bubble, space will contract, and behind it, expand. The ship itself inside the bubble will be in a state of rest, in a region of flat, undistorted space, like a surfer on the crest of a wave. That is, the crew will not experience any G-forces, but the bubble itself, this wave of space-time, can move at any, arbitrarily, high speed. The most interesting thing is that this does not violate the postulate of special relativity about the speed of light limit. This limit applies to the movement of objects inside space, and here, space itself moves. Nothing prevents space from expanding faster than the speed of light. Actually, this is exactly what, according to the Big Bang Theory, happened in the first moments of the universe's existence. And this is exactly what happens now at its farthest frontiers. The ship inside the Alcubierre bubble does not move faster than light locally, but its effective speed of travel from point A to point B can be superluminal. Sounds ideal, doesn't it? But, as in the case of wormholes, the devil is in the details, and these details are insurmountable. Firstly, to create such a bubble, to compress and expand space, that same exotic matter with negative energy density is again required, and in huge quantities. Alcubierre's initial calculations showed that creating a bubble around a small ship would require exotic matter with a mass equivalent to the mass of the entire observable universe. Later, other physicists refined the calculations, changed the geometry of the bubble, and were able to reduce the required mass to the mass of the planet Jupiter, and then even to a few hundred kilograms. But this still remains the mass of exotic hypothetical matter, which we do not know where to get and how to work with. Secondly, there's a problem with control. To launch the bubble, one needs to distribute exotic matter around the ship. But as soon as the bubble is created, the ship finds itself in causal isolation from its front wall. It cannot send any signal forward. After all, a signal cannot move faster than light to control movement or stop it. That is, to plot a course, it needs to be plotted in advance, even before the start. Thirdly, there's a huge problem with energy. Even if we found exotic matter, the energy needed to curve space-time is colossal. In addition, the front wall of the bubble will accumulate particles of the interstellar medium, accelerating them to monstrous energies. At the moment of arrival and turning off the engine, all this accumulated energy will be released in the form of a deadly beam of gamma radiation capable of sterilizing any planetary system at the destination point. That is, the arrival of a ship with a warp drive would be indistinguishable from a supernova explosion. Thus, both of these beautiful ideas, both wormholes and Alcubierre bubbles, although they are valid mathematical solutions to the equations of general relativity, run into seemingly insurmountable physical barriers. They require the existence of exotic matter that we have never seen, and energies that we do not possess. Perhaps they are merely pointers that our understanding of physics is still very incomplete. Or perhaps they are simply beautiful mathematical artifacts having no relation to reality. And this returns us from the heavens of theoretical dreams to the solid ground. If even the boldest ideas for hacking the universe turn out to be untenable, maybe we should reconsider the goal itself. Maybe the obsession with escaping Earth is an incorrectly posed task. And perhaps the history of our own species on our own planet has already given us a very visual and sad lesson on this topic. Let us leave space for a while. Leave Einstein's equations, star maps, and fuel calculations. Let us mentally transport ourselves to another point in space and time, to the very heart of the Pacific Ocean, to one of the most isolated inhabited pieces of land on our planet, to an island that its indigenous inhabitants called Rapa Nui, and we know as Easter Island. The history of this island is not just a local tragedy of a long-vanished people. It is a powerful, frightening metaphor, a model of what can happen to any civilization locked in a limited space with limited resources. This is a story that should sound like a toxin for anyone who dreams of cosmic expansion. Imagine, somewhere in the first millennium AD, a group of brave Polynesian navigators on their canoes, after a long and dangerous journey across the boundless ocean, find this uninhabited island. For them, it was paradise. Fertile volcanic soil, dense forests in which giant palms grew, ideally suited for building boats and houses, rich fauna, fresh water. They founded a new civilization here that was completely cut off from the rest of the world. Their island, just 163 square kilometers in size, became the entire universe for them. They did not know what was happening beyond the horizon and could not receive any help from outside. For several centuries, the Rapa Nui civilization flourished. The population grew, society became more complex, and in the center of their culture arose a grandiose, almost maniacal cult, the creation and installation of giant stone idols, moai. These multi-ton statues carved from volcanic tuff became a symbol of the power and status of various clans, which apparently competed with each other in who would erect the largest and most impressive statue. In order to carve, and most importantly, transport these stone giants from the quarries to the coast and install them on ceremonial platforms, colossal resources were required, primarily wood. Trees went into making levers, rollers, sledges, and ropes from palm fiber. And here, the countdown began. The island was small. The forests, which seemed inexhaustible, were actually finite. But society, seized by competitive excitement and religious zeal, continued to demand more and more moai. Tree after tree, grove after grove. The Rapa Nui people were cutting down their forest. They saw that there were fewer trees. They undoubtedly understood where this was leading. But no one could or wanted to stop this process. Cultural inertia, inter-clan rivalry, the belief that the gods and ancestors demanded new statues, all this turned out to be stronger than common sense. And then came the moment when the last tree was cut down. And at that moment, the world of the Rapa Nui collapsed. Without timber, they could no longer build big boats to go out into the ocean and catch fish, which was an important part of their diet. They could not build new houses. Soil erosion, no longer held back by tree roots, destroyed their agriculture. Food sources dried up. Society plunged into chaos. Wars began between clans, famine, cannibalism. The complex social structure that created great art degraded to a primitive struggle for survival. When the first Europeans arrived on the island in the 18th century, they found only pitiful remnants of a once great civilization living in caves among ruins and toppled statues. The Rapa Nui people found themselves trapped on their island. They exhausted all resources and they had no possibility to leave it. They saw the catastrophe approaching but could not prevent it. And now let us return to space and look at our own situation through the prism of this story. Our planet Earth is our Easter island. Yes, it is much larger, but it is also isolated in the boundless, hostile, and empty ocean of space. All the resources we have are here, on this blue sphere, and we, like the Rapa Nui people, are seized by our own version of the Moai cult. We call it progress, economic growth, consumption. We burn fossil fuels, cut down forests, pollute oceans, and the atmosphere with the same short-sightedness with which the inhabitants of Rapa Nui felled their palms. We also see that resources are finite. We also see the approach of ecological collapse. But our global civilization, spurred by competition between nations and corporations, cannot or does not want to stop. And in this situation, the idea of colonizing Mars or other planets begins to sound very familiarly alarming. For many, it has become a sort of modern version of the afterlife, technological salvation. It does not matter what we do to Earth, this idea says. After all, we can always escape to Mars. This is a most dangerous illusion. As we found out in previous chapters, escaping to Mars is not just getting into a boat and swimming to a neighboring island. It is a task of unimaginable complexity, standing on the verge of the possible, and maybe beyond it. Mars is not a spare paradise. It is a cold, dead, radioactive desert without air, water, or a magnetic field. An attempt to create an autonomous, self-sufficient colony there will require such technological and resource expenditures that are orders of magnitude greater than those needed to solve all our problems here on Earth. And this is where the Easter Island syndrome manifests itself on a cosmic scale. Instead of directing all our strength, all our intellect and resources to preserving and restoring our only unique home ideally suited for us, we spend them on a grandiose, but essentially senseless dream of escape. It is as if the Rapa Nui people, instead of planting new trees, spent the last logs on